This video is about using a Poisson approximation to the binomial. Situations can arise where the numbers get too large and too complicated for us to use the binomial, and if we're allowed to use a Poisson approximation, it's going to make life a lot simpler. So in what situations are we allowed to use a Poisson approximation? It's when n is large and when p is close to 0, then the binomial approximation, np, can be approximated by using a Poisson approximation lambda, where lambda equals np. So if n is large and p is close to 0, then we can use this approximation. Let's look at some examples. So here's our first example where we've got a binomial approximation with 1,000 trials and the probability of success is 0.003, and we want to find the probability that x is between 2 and 5. So is n large? Yes, it's 1,000. And is p close to 0? Yes, it's 0.003. Now we could calculate this directly using the binomial probability model that we've used, but we'll see that the Poisson approximation is a lot quicker. Firstly, let's consider what we're actually trying to find. We're trying to find the probability that x is between 2 and 5. It includes 2 and it includes 5. So we can work these out. We could work out the probability that x equals 2. That's going to be 1,000 C2 0.003 squared multiplied by 0.997 to the 998. And then we could do the same for x equals 3, same for x equals 4, same for x equals 5, and we'd get 4 probabilities which would add up to get our answer. And there'd be nothing wrong with this. This would be an exact method, but the Poisson approximation is going to be a lot quicker. Firstly, let's work out the expected value of x. That's just n times p, so that's 1,000 times 0.003, which is 3. So x is a binomial distribution, and we can say that y would be a Poisson distribution with parameter 3. So what we're after is the probability that x is between 2 and 5, so that's the probability that y is between 2 and 5. And we know that the parameter we're going to use is 3. So what we need to do is to find the probability that, as we said before, the probability that y is less than 5 minus the probability that y is less than 1. So we're going to need to use the tables. The parameter is 3, less than or equal to 5 is 0.9161, less than or equal to 1 is 0.1991, so we need to subtract those values. So carrying on our working from the last screen, we've got 0.9161 minus 0.1991, which is 0.7170. That's to 4 decimal places. And there we have it. Here's another example. It's just as easy, although the wording of the question is a bit odd. I suggest you pause the video and read through the question yourself just to make sure you understand it. So if x is the number of errors in the gene, then x has got a binomial distribution. The number is 200,000 because there's 200,000 base pairs, and the probability that it adds the wrong one is 2 times 10 to the minus 5. So what we're after is the probability that x is greater than or equal to 5. The expected value of x, which is n times p, that's 200,000 times 2 times 10 to the minus 5, that's 4. So y is going to be our approximation, Poisson approximation with parameter 4. So the probability that x is greater than or equal to 5 is the probability that y is greater than or equal to 5, which is 1 minus the probability that y is less than or equal to 4. It's either 0, 1, 2, 3 or 4, or it's 5 or more. So what we need to do is look up the tables with parameter 4, and we'll do that on the next screen. So our parameter is 4. We want the probability that y is smaller than or equal to 4, which is 0.6288, there it is, because we're in the 4 bit there, so that's the 4 there, it's 4 there. So carrying on our work from the last screen, we had 1 minus probability y less than or equal to 4, so that equals 1 minus 0.6288, which is 0.3712. Yeah, it's probably a good idea to give these figures to one significant figure, because the numbers in the original question were looked to be a one significant figure. If in doubt, give the full answer from the tables and then round off to what you think is appropriate. So it looked like quite a tough question, but by using the Poisson distribution, life became very simple.